Well, hi there. We're going to have a look at binomial distributions today, and they are fascinating and they are easy and they are rather fun. So they're like a little oasis in the complexity of life. I hope you agree when we get into them. I'm sure you will. Okay, let's go over the screen and have a look at them. Now, last time, guys, we learnt that the number of successes in a Bernoulli sequence of n trials is called a binomial random variable and is said to have a binomial probability distribution. Well, that's what we're dealing with today, a binomial probability distribution. Okay, so for a binomial random variable, we know that for n trials, if we have a probability of success of p, then for x successes, where x go from zero right up to the total number of trials, n, if capital X is the name we give for the number of successes, right? So we know that the probability that the number of successes, I'm just going to read that as the number of successes, equals a specific value will be NC that value times P to that value times 1 minus P to N minus the value. That's the formula we use. It's a bit abstract, isn't it? But look, it'll get clearer as we go along, okay? So, this is the deal. If we take every single possible value of the number of successes from 0 right up to n, one at a time, from 1 to n, from 0 to n, I mean, and calculate the probability that the number of successes equals that number of successes we're specifically choosing for this instance, for each occasion, from 0 right up to n, in other words, and then we plot these as individual points on a graph of x on the horizontal axis. X is the number of successes we're considering on the horizontal axis versus the probability that the number of successes will equal that value. On the vertical axis, we are plotting a distribution, a binomial probability distribution, guys, and that's what this session's all about, okay? So, just to make it a little bit more easier to understand, if p equaled 0.1, the probability of success was in any one trial was 0.1. We've got 20 trials. We can then tabulate and then plot the results of the probability that the number of successes will equal each value in turn that we're considering as a distribution. Now, under here, I've tabulated that whole thing for 20 trials and a probability of 0.1. Every single outcome of successes from 0 right up to 20. And that's the formula that I'm using. Okay, so the probability that the number of successes equals whatever I'm choosing for this particular calculation step would be 20c, that number, times 0.1 to the x times 0.9, which is the 1 minus p, to the 1 minus x. And here it comes, guys. Now you can do this just the same as I did it. In fact, it would be good practice if you did. Okay? There it is. So if you have no successes, for example, then the probability that you're going to get that x equals 0 will be 20c 0 times 0.1 to the 0 times 0.9 to the 1, right? That's what that one would be, and so on and so on and so on, using the same formula here for each of those specific values of little x, okay? Now, when I got down to here, I'm only doing them to 4 decimal places. It got 0 to 4 decimal places, so I didn't write 0.0000, I just wrote just 0. Was that alright? Yeah. Now, let's see what we get. Over the page we go, and I've graphed the whole thing for you. So that's now a graph of a probability distribution for that situation where n was 20 and p was 0.1. And you'll notice that I've got every single value of the number of successes plotted here, right, from 0 right up to 20. And the green dots, guys, are the values of probability, okay? Probability is on this axis here, number of successes on this axis here. And the green dots, so look for the green dots, there, and they get less and less and less down to infinitesimally small, which are plotted as zeros along here. Now, you're wondering, yes, I know, the elephant in the room at the moment is what are these dotted lines, for heaven's sake? Well, don't worry about them. They're nothing at all. They're just basically a method of just trying to point us to these green dots, you know, to make where the position of the green dots are on the page more obvious. They don't have any other significance apart from that. You see, the thing is with a binomial distribution, guys, these are discrete, random variables. You do not join the dots. It's not a continuous curve. These are just specific values which apply to these specific discrete number of successes, right? You can't have 3.5 or anywhere between 3 and 4, so you can't join the curve up between these dots. You just have to have discrete dots on a page. So if the dots tend to get a bit lost, so you do these little dotted lines here to sort of make it more obvious where the dots are on the screen or on the page where you're doing your graph. Do you get that? Yeah, that's all it is. Okay, it looks pretty cool, doesn't it? Now, I was going to point out to you too that this is very there's a very obvious trend here. You see how this peak here is at where x is 2, the number of successes is 2? Well, you think about that. Look, if the probability of success is 0.1, and you've got 20 trials, if you had 20 trials and the probability of success is 0.1, the number of successes out of those 20 trials is likely to be 0.1 times 20, isn't it? Which is 2, which is the most probable outcome. Yeah? That's the thing. That's the thing. So, and further to that, there's a very interesting trend which we can now observe. So if P changes, the shape of the distribution changes. So what are you saying, Wolfman? Well, funny you should ask. As P increases, so has this got to be, say, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, and so on, you would expect that the distribution moves, the peak of the distribution moves to the right, like a Mexican wave. Goodness gracious, a Mexican wave. And I'll show you that in a minute, and we all have to yell "Olé" together when I show you. Now, this is, say for example you had 0.8, probability of success in any individual trial as 0.8. Therefore, out of 20 trials, you'd be expecting 0.8 of 20, which would be, what's that, 16, wouldn't you? Of course you would. So therefore, you would expect as the probability goes up, therefore the number of successes out of the trial is going to go up, and therefore that's going to be reflected in the probability, which is going to be peaking over here somewhere as the probability goes up. Yes, that's what you'd expect. Do you understand what I mean? Yeah. Take for example when you're tossing a coin. You see, you would expect a 0.5 probability of getting a head. So out of 20 trials, you'd be expecting exactly half of those. See, 0.5 of 20. Successes, e.g. 10 successes, and that would be the most probable outcome, which you therefore you expect the peak to be at. For how many tosses did I say? For 10 tosses you'd expect 5 successes, wouldn't you? Yeah, or for 20 tosses you'd expect 10 successes. That's why the peak of probability will occur at that to reflect that, to reflect that probability. Now let's go with this. This is really cool. This is that same distribution where I've got a slider here where I can change the value of the probability 0.1 at a time. So that's 0.1, that'd be 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9. I'm going to show you from 0.1 all the way up to 0.9, and you're going to see the Mexican wave as the peak of the probability curve shifts, reflecting the changing probability, getting higher and higher as we go, okay? Watch this. Oh, wow. Now remember Olé, right? Olé! Did you like it? I think we should. It's so good we need to go backwards again. Look. Nice, isn't it? It's beautiful. Now, come on, we'll do another Olé together. Olé! Excellent. Olé today. Hooray! Now, let's go for some more information. So this Mexican wave phenomenon makes logical sense, yes, because if P is increasing, guys and girls, so too must the probability peak, move towards a greater number of successful trials. Yes, you see? So higher probability of success in each trial, it means that we're going to get a higher number of successful trials overall, aren't we? Yes, of course we are. And therefore the most probable, or the peak number of successful trials, therefore, will also move to the right. That's all we're saying. That's why you get the Mexican wave, okay? Here it comes again, look. Just won't go away, this Mexican wave. It's just so cool. So have a look. There it comes. And there it comes. And there it comes. And there it comes. There it goes. There it goes. And there's 0.9. See? It's beautiful, mighty fine at 0.9. So let's go with an example, and then we'll get out of here, and you can do some practice. Now, this is very simple. This stuff, it's just basically plotting. There's no smoke and mirrors, no skullduggery at all in this stuff. Very straightforward. That's what I was saying to you at the beginning. Now, what are we doing here? Probability distribution function, where n is 10, p is 0.2. We have to plot the individual values on a graph of the number of successes versus their probability on a graph, yes? From 0 to 10 in this instance. And in part B, we're doing the same thing, but in this case, n is 10 and p is 0.8. Yeah, that's all right. We're supposed to do them on the same plot, I think, on the same axis. I can't do that on my computer, so I'll do the next best thing for you, and you'll still see, you'll be able to compare them. No problem, we have to compare the distributions. Righty-ho. Now I'm going to do them CAS in this case. CAS is very cool. That's the formula for that one. That's the formula for that one. Would you agree? Yes, the only difference is that the probability for this one is 0.2, and therefore 1 minus p is 0.8. For this one, probability is 0.8, and 1 minus p therefore is 0.2, right? Now let's do the CAS thing, yeah? It's really, really cool. I'll show you the lists and spreadsheets, okay? And I'm going to get the spreadsheet to calculate the formula for the individual probabilities of each individual number of successes. Okay, so what is this? My goodness. Well, Wolfman, what have you done here? Well, this column here. This column here is for the 0.2 distribution. This column here is actually for the 0.8 one. Okay, so let's deal with this one here. This is the 0.2. Now, in each of these cells, they call these things cells. This has the formula put into it, equals binom PDF bracket. Now that 10 means 10 trials, comma. Then the next item here is the probability of success in any one trial, okay, which in this case is 0.2. And then that is the cell reference which contains the number of successes we're calculating the probability for in this instance. And I've got this cell here highlighted, this one here. Right, this is cell A. This cell A11. Now it's like a street directory. Look, here's 11 there, 11, and A is this column. So A11 means you go down there, across there, and bingo, you get cell A11. And that so in this particular cell we're calculating the probability of 10 successes, right? Because that's cell A11. Here, this address, cell A11 contains the number 10. Alright, that's what it is. So, here is X down here, the number of successes we're calculating the probability for, and here is the probability according to this beautiful formula. This is on the TI handheld, by the way. We use that at our school. Not plugging them, it's just that we use them at our school. So they are the cell reference numbers there. I've just written them in for you to make it clearer. Not that we're not going to do anything with it, just to make it clearer for you, see? They're the cell references, and this TI handheld, which I think the other one which we use in our schools, other schools use them, is the Casio one, which they would both have a fill down capability, which is really cool. You can just get the formula happening, say in this particular cell here. Then you can have a fill down where it'll just copy the same formula down here into every cell, except it advances this number here by one at a time, so it's actually referring to the correct cell for the number of successes we're expecting in each individual calculation done in each individual cell down here. So this would be referring to this would refer to cell A1, this would refer to cell A2, this would refer to cell A3, and it all just does it automatically right down to cell A11. It's truly amazing. Spreadsheets are the most marvellous beasties ever invented, I think, especially for accountants. They love them. Now, yes, just to explain to you, this here is the number of trials. This is the probability of success in any one particular trial, and this is the reference to, in this case, this cell here, which has the number of successes we're calculating the probability for. Okay, now let's go over the screen and we will show you the curve. There it is. It's nice, isn't it? So that's probability, that's the number of successes. where PR is 0.2 and the number of trials is 10. And of course we are expecting, out of 10 trials, we would be expecting 2 successes, and of course that's the most probable outcome. There you get it, see? Yeah, it's beautiful, isn't it? Now, okay, let's go over and do the other one now, part B. Same thing, except in this case PR was 0.8, as you can see reflected in this formula, and we're dealing with this column now. Okay, this column. So 10 trials, 0.8, and in this case I'm referring to cell A1, which, in other words, for this particular, this number here is the probability for 0 successes, okay? Which for a probability of 0.8 would be pretty low, and that's what we've got, you see? That's what we've got. So I'll just reveal all the rest of this stuff here. That's the formula. There are the cell numbers, that's the fill down thing again, and yes, that's the same explanation there. The number of trials, the probability of success in any one trial, and the number of successes, the cell reference to where the number of successes is written, okay? So that we can then advance that down with a fill down capability most marvellously. Yes, now we're going to go over the thing and look at the graph of it. Here it comes, guys. There it is, right? And of course, that's PR there, that's X there, and this in this instance, PR, the probability of success in any one trial was 0.8, and there were 10 trials, of course. And as we would certainly expect, for 10 trials with a probability of 0.8, you'd be expecting 8 successes, wouldn't you? And that's the most probable outcome. See? That's how the Mexican wave occurs. Now, I think that's just about it. Now, I was not able to plot them on the same thingy because my computer won't let me do that, but I did them side by side for you, okay? So there they are. There they are. Beautiful, aren't they? And yeah, that's just summarising. This was, N was 10, P was 0.2 for any one, the probability of success of any one trial, and that's the formula that I used to calculate all of these individual values of X plugged in there. That's what, and the probabilities that I got, that's the probabilities that I got plotted there. Right? Actually, I got the computer to plot them, I didn't do it. And this over here, this blue one, there it is. So yeah, you got N equals 10, P is 0.8, right? And there's the formula, and that's probability along there, that's X along there, the number of successes. We're calculating the probability for, and the formula is different because it's probability of success in any one trial is 0.8, whereas over here is 0.2, and of course, probability of 0.8 out of 10 trials, we would be expecting 8 successes, and that is the most probable outcome. You see, that is the most probable outcome. It all makes sense. It hangs together beautifully. Now, in the next video, we're going to do measures of centre and spread for binomial distributions. We're going to do the expected value and the variance, and they're really, really easy. You're just going to love them. So stay tuned for that. And in the meantime, you're a star, and huzzah, you will go far if you do some practice and have a good time with it. And thanks for coming to see me today. All the very best and have a great day.